Students, Saxon Algebra 2, Lesson 107. We are going to go back through the archives of your brain, and we're going to look at numbers, and we're going to talk about place value for just a minute. You know now, as you probably knew then, that this is a 4 and a 7, but when we put them together like this, they have a special meaning. This we call the tens place. And what it means is that 4 doesn't really just represent 4, it represents 4 times 10, the value of its place, so that this number actually represents 40. And we know that this is what we call the ones place, or sometimes it's called the units place. Same difference. This, again, doesn't just represent a 7, it represents 7 times the value of its place, which is 1. And so the total of these is a number that we call 47, and it represents, let me just show it like this. Oh, I already did. 40 plus 7 equals 47. Okay. So we know that place value means a lot if we are trying to create the values of these numbers. Now, what we're going to do is we're going to work a problem where we want to set up variables not only for the original number, so we're going to abbreviate this as T and this as U. We're going to use the U so that we're not using the O, because an O looks like a 0, that's confusing. So we're going to say that 10 times the number in the tens place plus 1 times the number in the units place is an expression for what John will often call the original number. That's a way we can write any number in algebraic form if we don't know the digits. Okay? So in this case, we would say that T equals 4 and U equals 7. So our number would be 10 times T, which is 4, plus 1 times U, which is 7, and that would be 40 plus 7, 47. Okay, so we can see that this works. Okay, now what if we wanted to reverse the digits? Okay, what if we wanted to take this number and reverse it so that 47 becomes 74, right? Look what's happened in terms of our variables. The number that we're calling T is now in the ones place, and the number that we're calling U is now in the units place. So if we wanted to write this, we would say 10 times the units place plus 1 times the tens place. That gives us what we call the number with the digits reversed, or what John will sometimes call the new number. Okay? In his problems, he's going to refer to the original number and the number with the digits reversed, or the new number. Alright? So these are the algebraic expressions we are going to use to do that. And let me just prove that this one works. Okay, 10 times U would be 10 times 7 plus 1 times the tens place number, which we said was 4. And so that's 70 plus 4, 74. So we can reverse the digits and come up with an algebraic expression that will tell us how to do that. All right? Now, let's look at how this works in a problem. This is going to be super helpful to us. Example 107.1. The sum of the digits in a 2-digit counting number is 11. Okay, well, if we were using our example, we would say that, okay, 4 plus 7 equals 11. We're not putting any value on these, we're just adding up the digits. The way we would write that, using these digits that we have, is we would say T plus U equals 11. And in this case, it's true. I chose my numbers carefully. And then we also want to say that if the digits are reversed, the new number is greater than the old number by 27. Okay, so if the digits are reversed, that means we want to start using these expressions. The new number is greater than the original number. So the new number we write like this, 10u plus 1t. That new number is greater than the original number by 27. So we want to add 27 to the little side. And now they're equal. Okay? This we don't need. That was just us talking about what the sentence meant. Okay? So here is a system of equations. And notice that this is kind of like our coin problems or some of the other systems we've done, where this is more of a quantity statement and this is more of a value statement, where we're multiplying the value of each unit by its place value. Okay, so now we can carry on our work with substitution. We're going to substitute this little guy into this big thing. But look at this. We can clean this up first. And John doesn't always do this, but I like to. I like to subtract 1t from both sides. And I like to subtract 1u from both sides, so that I don't have all those extra terms floating around. Gone, gone. 9u equals 9t plus 27. Okay, we cleaned that up. And then let's do this. Let's just subtract the u. We could subtract the t too, it doesn't matter. But if we subtract the u, we'll get t equals 11 minus u. Okay, so we're going to carry these forward to the next page and continue solving our system of equations. Let's see if I can remember them. Equals 11 minus u, and then we had 9, let's see which letters first, 9u equals 9t plus 27. Double check it one more time, make sure I didn't copy it wrong, because that would be really annoying, wouldn't it? Okay, we're good. This is a system. And the book is centered again. Okay, so we can look at this and go, all right, we don't want to try to eliminate, we want to substitute. So we'll substitute A into B, let's call it A and B. And that will give us 9u equals 9 times 11 minus u plus 27. Okay, 9u equals 99 minus 9u plus 27. Let's add 9u to both sides, and we'll combine the like terms. And we'll get 18u equals, that cancels, 99 plus 27. Was 126. And this I'm pretty sure goes in here 7 times, because 8 times 7 is 56. That would give us the 6. So let's just test it. 18 times 7, 56, 5, 7. Okay, that works. So we get that u equals 7. Okay? Now we need to solve for t. And we can go right up here and see 11 minus u equals t. So that would be 11 minus 7, and this would be 4. So that means our original number equals 47, which, funnily enough, is the number that I just randomly chose out of my head to start this lesson. That's funny. It just worked out that way. But the answer to our problem is 47. This is confusing and a little bit hard because you have to wrap your mind around these two weird equations as to how we can write numbers. So let's do the next problem. This is the last problem for lesson 107. And let me write this up here again. Our original number, as John uses that expression, is 10 times the digit in the tens place plus 1 times the digit in the units place. That's normal. Then when we get weird and we reverse it, when the digits are reversed, sometimes he refers to it that way, and sometimes he'll say the new number. That's when we flip it and make it weird. 10 times the digit in the ones or units place plus 1 times the digit in the tens place. That's the one that would have made you flunk second grade if you would have written that. And thank goodness you didn't flunk second grade. But in any case, this is the one that looks really weird because it is reversed. Okay, let's do this one. 102. The sum of the digits of a two-digit counting number was 9. Okay, this is the easy one. The sum of the digits means we take t plus u, we add them up, and we get 9. This is what we call like the quantity statement. Next will come the value statement, which is that when the digits are reversed, the new number, 10u plus 1t, that represents the new number, was less than the original number. It's okay if you refer to your notes on this in the first lesson or two, but after that, I don't even want you to memorize this. I just want you to be able to recreate these formulas using your understanding, using logic, right? You don't have to memorize them per se, you just can understand. Normally we multiply 10 times the tens place and 1 times the units place, and if we reverse it, it looks like that. Okay, when the digits were reversed, the new number was less than the original number. Okay, I've written the inequality, now I have to fix it. When the digits were reversed, the new number was 45 less than the original number. So this is the big side. I'm going to subtract 45 from him, and now we're equal. What was the original number? Okay, here's our system. I would like to clean this one up first. Subtract the 1t, subtract the 1u. It'll always be like this, you guys, where we have to clean it up first. So then we get 9u equals 9t minus 45. All right. This time, just to make it different, let's solve for u. So we'll subtract t from both sides. U equals 9 minus t. That's what we'll substitute into this. So we'll do 9 times 9 minus t equals 9t minus 45. John substitutes before cleaning this expression. It gives me a headache. It's too messy. I like to neaten that up first. And it'll work out just fine. Okay, so we substituted that properly. Oh, I have to go in, sorry. 99, no, 9 times 9 is 81, sorry. Minus 9t equals 9t minus 45. We're going to add 9t to both sides. And then let's add 45 to both sides. And we get, this cancels, 18t equals, oh, that's funny, 126. This is the same division we had in the other problem. And we know that 18 times 7 equals 126. I'll prove it to you over here. 56. 5 plus 7 is 12. Okay, so t equals, what did I just say? 7. But we don't have the very same answer as last time, because this time our digits add up not to 11, but this time our digits add up to 9. So this must be 2, right? Because it's 11 minus, oh no, I'm sorry, I'm confusing the last problem with this one. It's 9, the total, minus t, which is 7, so that means the units number must be 2, and so our original number which is what John asked us to solve for, equals 72. That's it. Lesson 107. A little bit confusing. Try a few, see if it makes sense.